So hopefully you printed this file off from above the video because I'm going to refer to the formulas on it as we work through, and I'm going to do some explanation first. Now it's important to note that I don't expect you to have these formulas memorized, that you can come back and take a look at the formulas themselves whenever you're doing these types of questions. So the first thing we're going to look at is projections, and we've actually done this before. When we looked at vectors and we looked at their vertical and horizontal components, we were really projecting them onto a horizontal line and projecting them onto a vertical line, because a projection is like a shadow. So if I have two vectors, and I'm going to call this one U and this one V, I'm going to call O the origin, or where they're connected, and I'm going to have a vector ON, and it's as if I'm shining light straight down onto here, and I'm going to get a shadow. So N is going to be the point where U shadows onto V. So I'm literally projecting U onto V and seeing where it lands. So the vector from O to N represents the projection of U onto V, and it's found by doing U dot V, which gives us a scalar, divided by the magnitude of V squared times V, because this is going to give us a vector. U dot V is a scalar. The magnitude of V squared is a scalar, so I have a scalar divided by a scalar, but then I'm multiplying by the vector V. So if the angle is less than 90 degrees, it's easy to see. I can also project onto if the angle between them is not 90 degrees. So I have U in V. O is still where they meet, but in this case, my N is going to be behind the vector V. So when I do this, I'm going to end up getting a negative because it's actually in the opposite direction of V, but I would still use this formula. This gives me a vector. If I'm looking for the magnitude only, so I just want to know how long is the projection going to be, I can use this formula. It's U dot V, the absolute value of that, because I don't want direction, I just want size, divided by the magnitude of V. Or another way to find it is the magnitude of U times cos of theta, where theta is in between them. And I'm going to do some examples and show you how to use those formulas. Now, whenever you have two vectors U and V, put this over so you can see, we talked about this when we were adding geometric, that I can make a parallelogram out of them by moving U over and by moving V up. So the area of that parallelogram is going to be the magnitude, because remember that's what those lines mean, of the cross product. So if you do U cross V and take the magnitude of it, it's going to give you the area of that parallelogram. Now, a parallelepiped is if I'm in 3 dimensions and I really have 3 vectors, and I'm going to call them A, B, and C. If I extend all those vectors out, and again, 3-dimension is not my strong point when I'm drawing in it, but if I slide all those vectors around, I'm going to get a 3-dimensional parallelogram, which is called a parallelepiped. If I just wanted the area of the face, I would just have to do A cross C in this case. I said B was the one in the middle because it's just the one on front. But if I want the volume of the whole parallelepiped, I do 2 of them, I cross them together, B cross C, and then I take the dot product with the third. Now, the cross product, it doesn't matter the order what we do them in now. You're going to pick 2 vectors and cross product them, and then dot that resulting vector with the third, and take the absolute value of that, and that's going to give you the volume. The volume doesn't change no matter which way I orient this or which way I put the vectors together. And because we're looking for the absolute value or the magnitude, the order isn't important. We can also look at work. Work is a scalar, and the unit for work is joules. If you have any background in physics, this should be familiar. If you don't have any background, it's okay. We're going to learn to work with this. So work is the dot product between the force and the displacement. So the force is how much force I'm using to move something, and the displacement is how far I move it. But we also have a formula for dot product that is the magnitude of F times the magnitude of D times cos theta, where F is the force that's acting on the object, D is the displacement, and theta is the angle between the force and the displacement. So the force is going to be measured in newtons, and the distance is going to be measured in meters. and that will result in a unit that we've called joules. Torque is now when I'm spinning something, and torque results in a vector. So if I push on a wrench and I'm tightening a bolt, the bolt is moving, but it's also moving down or into whatever I'm tightening it into. So it's following a direction. I can measure the amount of force I'm applying to it, and there's a result to that, but that resultant has a direction. Either the bolt is going into the object or tightening, or coming out of the object, loosening. So torque is a vector. So now it becomes the cross product. So I have R times F, and which is R times F times sine theta times some little unit vector n that's in the direction. But most of the time when we talk about torque, we do just want the magnitude. So if I just want the magnitude or the amount of torque, I can drop this little vector at the end, and it's R times F, magnitude of R times the magnitude of F times sine theta. That should look familiar because that's another way to find the magnitude of the cross product. So in this case, F is the applied force, going to be measured in newtons. R is the length of the lever arm. It might be a wrench, it might be a pry bar, it might be a pedal length, but it's going to be measured in meters. Theta is the angle between R and F, and if I apply this little n, it just means that that's the vector in the direction of going into or out of if I'm talking about a bolt. But a lot of times we just kind of ignore that and we talk about the magnitude of the torque. Okay, so let's work with these formulas. And again, I can't stress enough that you don't have to have them memorized, that I would expect you to use this reference sheet to go back and pull the formulas that you need. So question number 1, find the projection of u onto v if u is 8, negative 1, 2, and v is negative 1, 5, 4. So they've asked for the full projection here. This says nothing about magnitude, so I'm going to go up and grab this full formula. So the projection, which is from where they meet, which I'm going to call O, to where the projection lands, which I'm going to call N, which is the projection of u onto v, is u dot v times v over the magnitude of v squared. I just grabbed the formula from the top. Now, order is important. If it's u onto v, v is the last part of everything. If I wanted the projection of v onto u, I would switch the order of u and v. It's really important that the one you're projecting onto goes at the end. So I need a bunch of things for this. The first thing I need is u dot v. Well, I have u and I have v, so I'm going to do u dot v by doing 8 times negative 1, which is negative 8, plus negative 1 times 5, which is negative 5, plus 2 times 4, which is 8. So that's going to give me negative 5. Now I'm going to find the magnitude of v squared. Well, the magnitude of v is going to be the root of 1 plus 25 plus 16, which is root 42, but that's the magnitude of v. So when I square it, it just becomes 42. So now I'm going to come over here. U dot v is negative 5. V squared is 42. And I'm going to multiply that by v. So I'm going to take negative 1, 5, 4. This is scalar multiplication into a vector, which means I just distribute this in. So I'm going to end up with positive 5 over 42, negative 25 over 42, and then I'm going to get negative 20 over 42, but I don't want to do a whole other step, so I'm going to reduce that to negative 10 over 21 now. So this would be the vector that would have u projected onto v. So basically the shadow on u on v would land at that point. Question number 2. Find the area of the triangle with vertices 7, 2, negative 5, 9, negative 1, 6, and R, 7, 3, negative 3. Here's the important thing. Those are vertices. They are not vectors. It is in 3 dimensions, but I'm just going to set them up so I have P, Q, and R. Doesn't matter where they go. I'm going to put the ordered pairs with it. So 9, negative 1, 6, P is 7, 2, negative 5, and R is 7, 3, negative 3. I'm going to cross two vectors. I'm going to call that U, and I'm going to call that V. This triangle is 1/2 of the parallelogram that would be created with U and V. So it's going to be 1/2 of the formula, and if we go back to the first page, the area of a parallelogram is the magnitude of U cross V. So now I need to find U and V. They need to be locked tail to tail, so I have to backwards subtract. So 9 subtract 7 would give me 2. Negative 1 subtract 2 would give me negative 3. And 6 subtract negative 5 would give me 1. So vector U is equal to 2, negative 3, 1. I'm going to find vector V. It goes from P to R, so I have to backwards subtract. So 7 subtract 7 is 0. 3 subtract 2 is 1. Negative 3 subtract negative 5 is positive 2. So I want 1/2 of the magnitude of U cross V. If it was the whole parallelogram, I would just want U cross V. It's a formula from the first sheet of the handout. So now I need U cross V. I could do the R, or the magnitude of U, magnitude of V, sine theta, but I need that. I'm just going to do the straight cross product. So I'm going to take my U and my V and cross product those. So I'm going to go 2, negative 3, 1, 2, negative 3, 1. 0, 1, 2, 0, 1, 2. So again, this is the trick we use for doing the cross product. I cross off first and second, and now I'm going to do all my subtractions. So I'm going to have 1/2 of the magnitude of negative 6 subtract 2, which is going to be negative 8. So I did negative 3 times 2, subtract 1 times 1. 0, 1 times 0, subtract 2 times 2 is going to give me negative 4. 2 times 1, subtract negative 3 times 0, so it's going to give me 2. So now I want the magnitude of this vector. Well, the magnitude is just using extended Pythagorean theorem. So it's going to be 64 plus 16 plus 4. So that's going to be 84 root over 2. Well, we always reduce our roots into lowest terms. 84 is, does 16 go into it? No, but 4 does. 84 divided by 4 is 21. So that's root 4 times 21 over 2, which is 2 root 21 over 2, because the square root of 4 is 2. So the area of that triangle, is root 21. If I was looking for the whole parallelogram, I would drop the 1/2 and just use the magnitude of U cross V. Okay. A 25 kilogram crate is pulled up an 8-meter ramp that is inclined at 16 degrees to the horizontal. Find the work done by gravity if the crate slides back down the ramp. So when we were looking at forces of vectors, we started to look at making situation diagrams and then force diagrams. So there's my horizontal, there's my ramp. So there's 18 degrees there. I have a 25 kilogram object, and it's going to slide 8 meters down the ramp. Gravity is always acting perpendicular to the horizontal, but the result is it's going to slide down the ramp. I can find the magnitude of gravity because I have the 25 kilograms. It's 9.8 per kilogram, so I do 25 times 9.8, so it's 245 newtons. So if I just look, there's my displacement vector, which is this one here. There's my gravity vector. I need the angle between them, because the angle between them in the work formula, because work is the magnitude of the force times the magnitude of the displacement times cos of theta, where theta is the angle in between them, tail to tail. Well, here are those two vectors on this diagram. If that's 18 degrees, I have 72 in there, because 180 subtract 90 subtract 18. So 72 degrees is the angle between gravity, which acts vertically, and the displacement, which is acting down the ramp. So now I just fill this in. So I have 245 newtons times 8 meters times the cos of 72. I type that into my calculator. And it's 606, if I round, joules, because the unit for work is joules. Now, if the crate needs to be pulled back up the ramp, what's the minimum amount of work that must be done? The pulling force is applied 40 degrees to the horizontal. So there's my ramp. So you need to see that. Here's my 18 degrees. There's gravity that wants to pull it, and I'm going to put my crate there. I'm not going to make it round, I'm going to make it square. The result of gravity pulls it down there. We want to pull it back up. Okay, so this is the force that needs to be acting on it. But they said the force is actually acting 40 degrees to the horizontal. So there is a horizontal in here. The ramp is 18 degrees to the horizontal. There's 40 degrees between the force that's pulling on this object and the horizontal, so I know that that's 22 degrees. So this is my force that's being applied, and this is what happens to it. I'm going to change that from applied. Now, if we want to do the minimum amount of work, the force that we're applying here has to counteract just bare minimally the gravity that's pulling it down. But we're applying here, and the effect is going to be pulling it up. Gravity is working here, but the effect is falling it down. So we're really going to look at projecting. We're going to take this applied force and project it onto the line that's parallel to the ramp, or the axis of movement. I'm going to take this gravity and project it, because that's what's happening, and those projections have to be equal. So the force that we apply projected onto the displacement, which is the ramp, has to be the same as the force of gravity projected onto the ramp. Now, if we go back to our projections, if I want to find a whole projection, I have to do the vector. But I really just want the magnitude. The magnitudes have to be equal. Pull it down, then pull it up to counteract it. So I can just use the magnitude of u times the cos of theta. So Fa is the magnitude of the force I need to do, but then it's going to be times the cos of 22, because 22 is the angle between the force and the ramp. That has to equal 245, because from up here, we know that gravity in this case is 245 newtons, because it's still the 25 kilogram trunk, times cos of 72, because 72 degrees is the angle between gravity and the displacement down there. I can solve this, that the magnitude of the applied force is 245 times the cos of 72 divided by the cos of 22. I don't know what that is, but my calculator does. 245 times cos 72 divided by cos 22 is 81.782 newtons. So in order to counteract gravity, it's going to take 81.7 newtons of force applied 40 degrees to the horizontal, or 22 degrees to the ramp, to pull it back up. And the last question, a biker is able to pedal with a force of 115 newtons, 15 degrees to the vertical. The shaft of the pedal is 16 centimeters long, and the shaft is currently 25 degrees to the horizontal. Find the amount of torque applied by the biker, because the biker is pushing down and that's creating a spinning or a torque. So I'm going to try and get sense of this. I'm going to draw my pedal, which looks like that. So that's the foot part of the pedal. The pedal is 16 centimeters long, but whenever we work with these formulas, our units are newtons and meters. So right away I'm going to change that to 0.16 meter. Now this is the force coming in because the foot is there. So the biker is applying 115 newtons of force 15 degrees to the horizontal. The shaft of the bike is 25 degrees to the horizontal. So I think I have everything in there. Now, if we look at torque, whenever you're applying to a lever and something's going to turn, it's a torque formula. And the magnitude of the torque is R times F times sine theta. R is the length of the lever in meters. So in this case, that's 0.16. Force is the amount of force being applied, which is 115 newtons in this case. Theta is going to be the angle in between your force and your lever. So now here's where I need to figure out what's happening, and I need an angle. So I'm going to draw just a different diagram so I can put all my angles on it. So here's my horizontal, and the lever is 25 degrees to the horizontal. Here's my vertical. Again, I'll move this up so you can see it. So there's my horizontal, and I was told that the lever is 25 degrees to the horizontal. Here's my vertical, and I was told that this is 15 degrees to the vertical. My force is 15 degrees to the vertical. I need the angle in between my force and my lever. Well, if that's 90, that has to be 65 degrees because vertical and horizontal makes a right triangle. Vertical gives me 180 degrees on both sides. So if I do 180 minus 15 minus 65, I get 100 degrees. So theta is 100 degrees. And there might be some people who are comfortable enough working up off of here. They extend that down. They get 90, 65, and 100, and that's fine. But there's nothing wrong with pulling it out and trying to figure out the angle. And again, it's just the amount of torque. So that is magnitude. We just need a number. So I'm going to do 0.16 times 115 times sine of 100, and it's going to be 18.1 Newton meters because that is the unit for torque because we're applying a force in newtons to a lever which is in meters, so we say it's in Newton meters.